I'm an opera singer, as well as a cognitive neuroscientist, and this duality is often surprising to people meeting me for the first time. They wonder how I can switch back and forth between the two callings. Yet for me, it's no less difficult to go from science to singing as it is to switch between any two dissimilar tasks, like writing and teaching, for example. Sure, it takes me a moment or two to refocus, but for many people, the idea that a person can be proficient in both art, reserved for right brain dominant people, and science, where the left brain steers the ship, seems nearly impossible. Yet for centuries, scientists and artists were virtually indistinguishable in many ways, and many of them dabbled in both disciplines. There is overlap in terms of the skills required to succeed in either field: attention to detail, creativity, risk-taking, and dedicated diligence, to name just a few. But in the past century, people have gone so far as to suggest that the two jobs are driven by different hemispheres in the brain: the logical, left-sided scientist and the emotional, right-brained artist. Is there any truth to the idea that we have a dominant hemisphere, whether it be the right or the left, and that left-dominant people are less creative than right-dominant ones, or more logical? What's more, does tapping into your right hemisphere make you more creative? These are the myths that we'll be evaluating in this lecture. Sometimes, people who are coaching artists feel the need to justify their techniques. Rightly so, as coaches are expensive. It's a competitive market, and artists, especially performers, need to constantly work on their skills. And sometimes they do so by referring to psychology or neuroscience. Sometimes they're right, but oftentimes, peppering a little neuroscientific jargon into an explanation might make it sound more impressive, but not actually be based on fact. One idea that has been overused and misinterpreted by many laypeople is the notion that the left side of your brain is logical and analytical, while your right side is creative, and that instead of working together, these two hemispheres are in competition with one another. The logic then goes that if you can tap into your right brain, releasing it from dominance by the left, you can be more creative. Or that you need to shut down your overbearing left hemisphere in order to do something original and artistic. Where did this idea come from? Is any of it based on scientific evidence? There certainly is evidence that patients with specific lesions to one side of the brain may show a different symptom profile from patients with comparable lesions to the other side. The brain is to some extent modular, in that different brain regions are assigned different roles. But the truth is, of course, much more complex. Take language, for instance, which many people associate strictly with the left hemisphere. As far back as the 19th century, European physicians Paul Broca and Karl Wernicke noticed that their patients, who had circumscribed lesions in the left hemisphere, showed a peculiar symptom profile. Broca's patient was nicknamed Tan because that was one of the very few words that he could say, and he seemed to have little trouble understanding speech, but had great difficulty producing it. By contrast, Wernicke's patients, whose brain damage was just a little bit below the area where Tan's was, were able to produce speech, but when they did, it sounded like word salad, gibberish. They had trouble with speech comprehension, whether it was understanding what someone else was saying or saying something themselves. Studying such groups of lesion patients, then, helped neuroscientists discover that certain cognitive functions, like language, are localized primarily to one side. This assignment of different functions to the two different hemispheres is known as lateralization. When it comes to our senses and actions, in particular, the two sides of the brain do process different sets of information. The left side of space is represented primarily in the right hemisphere, and vice versa. This means that your right hand is controlled by the left side of your brain, and what you see in your left visual field is projected to the back of the right side of your cerebral cortex. It's this fact that I've heard some acting coaches use to justify a technique designed to make a person more creative. Engage the left side of your body, they say, and you'll tap into your creative right brain. But there are a few assumptions that such an explanation glosses over, most of which aren't true. Just like you have a dominant hand, most likely you also have a dominant hemisphere. Or I should say, because you have a dominant hemisphere, you also have a dominant hand. Neuroscientists are still working out the details of how related the lateralization of cognition and handedness really might be, and how they develop. And the story is getting more complicated by the day. But for most of us who are right-handed, our left hemisphere is our dominant hemisphere, and the left side of our brain contains most of our language function. And people sometimes point to left-handed individuals, claiming that they're more likely to be engaged in creative careers than right-handed ones, and that surely must be because they're dominated by their right hemisphere. But if you're left-handed, then there's only about a 20% chance that your right hemisphere is your dominant hemisphere. And there's also a 20% chance that both of your hemispheres contain language function. As for the rest of the lefties, they've still got about a 50 to 60% chance that most of their language function is on the left side. So already, as you can see, even for language, arguably the star of lateralization, the story isn't quite as neat as we would like it to be. And even though many language functions rely on an intact left hemisphere, as Broca and Wernicke noted, the right hemisphere certainly participates in verbal communication. The right side is much better at deciphering prosody and accentuation, while the left is the home of the grammar police and the dictionary. For example, in both sets of patients, the physicians and their colleagues noticed that some aspects of speech were relatively preserved. Prosody, for example, the music of speech, seemed to be retained. In other words, their speech contained the appropriate ups and downs of conversation. You could hear the emotional intent in the melody of their speech. But patients with right hemisphere damage can show deficits in prosody. They have trouble distinguishing and expressing modulations in speech. Aha, you might say, if there ever was an artistic side to language, surely it would be prosody. But I suspect that many a great writer might take issue with that stance. So what else does the right hemisphere do that the left does not? And how do we know? Before the explosion of neuroimaging research, studying patients with lateralized lesions or commissurotomies was the best way we had to figure out what the two sides of the brain might be doing. We'll get back to that in a minute, but tracking activity in the brains of healthy people while they're engaging in different tasks, as we do with neuroimaging, provides another, perhaps more modern window into laterality. For example, neuroimaging studies suggest that the two hemispheres might play different roles in emotion processing, with the left hemisphere showing somewhat greater activation for happy or positive emotions, and the right hemisphere showing more activity during negative emotional processing. One particularly interesting insight that neuroimaging has given us is the finding that white matter tracks, or the wiring diagram of the two hemispheres, is different. The wiring of the right hemisphere has been called more efficient because it has greater connectivity between regions. Think of a city with a really good subway system like Manhattan, making it easy to get from one side of the city to the other. The left hemisphere, in contrast, seems to be more modular. It's more like a cluster of little cities operating more independently, like Los Angeles, where every mini-city has its own municipal transport system, and the cities themselves are not well connected. Santa Monica and Beverly Hills have different governing bodies, so it's hard to get from one to the other using public transportation. It's this wiring difference that might explain why the left hemisphere seems to contain regions that operate somewhat more independently and are more specialized than the regions in the right hemisphere, which are involved in more integrative processes like visuospatial tasks, recognizing faces, for example, or arranging a set of blocks to match a pattern, or paying attention to all of space, not just one side of it. So it's easier to find specialization in the left than the right hemisphere. And here too, people looking for evidence for the association between the right brain and creativity and the left brain and logic point to these wiring differences. If the right brain is more interconnected, does that make it easier for it to generate new ideas, finding new connections between remotely associated concepts? Not so fast. Neuroimaging research has also shown us just how communicative the two hemispheres are. Unless that connection between them is physically severed, information is zipping across the hemispheres during the vast majority of tasks that we ask our brains to accomplish. And in many regions, signals pass from one hemisphere to the other more quickly than they do within a single hemisphere. That is, some signals from the left and right prefrontal cortex can be exchanged more efficiently than signals from the back to the front of the brain in the same hemisphere. So, engaging my left arm in an acting exercise doesn't mean that my right hemisphere is now dominating all the other processes that my brain is working on. It might help me become less inhibited and have other psychological effects, but it's not going to suddenly make me pay more attention to prosody, for example, just because I'm engaging my right motor cortex. To understand what underlies the left-right brain myth, why it's wrong, and how much more interesting the truth is, we need to go back to a time before neuroimaging, with the psychologists who were among the first to suggest the two hemispheres of the brain, left and right, might play different roles. And this trip through time takes us to the 1940s, when two neurosurgeons attempted an experimental procedure to help curb seizures in patients with severe cases of epilepsy. Seizures are caused by the spread of abnormal electrical activity in the brain. Usually, this activity starts in one part of the brain, and like unchecked wildfire, it spreads across the brain, following the trajectory of neural pathways. When this electrical activity is severe enough and widespread, people with epilepsy experience dangerous and debilitating seizures. Now here's a bit of neuroanatomy for you to consider. Picture the brain as an ice cream cone. The brainstem, where your vital functions like breathing and heart rate are controlled, is the cone. One scoop up is the midbrain, and here, already, we see the division into two sides of the brain, with many structures coming in pairs, one left, one right. The top scoop is the cerebral cortex, which is also divided into two hemispheres. Now, let's say that the abnormal electrical activity starts in one part of the brain because a set of cells are misfiring. Then, it begins to spread along the connections and eventually sets the whole brain misfiring. That's a seizure. In the 1940s, neurosurgeons reasoned that if they could contain the electrical misfiring to only one side of the brain, the seizures wouldn't be as severe. But the imaging tools that were available to them at the time were pretty limited. It was hard to figure out exactly where the seizures were starting. So they proposed a surgical procedure that would sever the corpus callosum. This is the information superhighway that connects the two cerebral hemispheres of the brain. By cutting this fiber tract, they believed that they could trap the abnormal electrical activity in one hemisphere. Unfortunately, these initial surgeries had no positive effect on their patients, and the technique was quickly abandoned until the early 60s. That's when other neurosurgeons working with seizure patients realized that the idea of severing the connections between the two hemispheres of the brain was actually sound. The problem with the initial experiments was that the technique itself was flawed. You see, in the first surgeries, only the corpus callosum was cut, but there are actually two other routes through which abnormal neuronal activity can transfer from one side of the brain to the other. These are the hippocampal and anterior commissures. These neurosurgeons performed new surgeries that severed these additional routes along with the corpus callosum. The neurosurgeons called these new operations commissurotomies, and they found that these procedures successfully curbed the spread of seizures in a number of severely epileptic patients. Their success came from being able to fully sever the communication between the two halves of the brain. We don't do this surgery very often anymore because the drugs available for curbing epilepsy are much better than they were in the 60s, and less invasive surgical procedures have also been developed. But around the same time, a neuropsychologist named Roger Sperry together with his student Michael Gazzaniga, began testing these so-called split brain patients to find out what aspects of the human mind are processed in each hemisphere of the brain. This pioneering work ultimately won Sperry the Nobel Prize in 1981, and Michael Gazzaniga went on to become the father of cognitive neuroscience. But it also seeded the left logical, right creative brain myth. Once neurosurgeons began performing commissurotomies, they started producing patients with left and right hemispheres that could no longer exchange information. So this means that what their left brain knows, their right brain might not, and vice versa. Realizing this was the case, Sperry, Gazzaniga, and other investigators began devising novel ways to query one half of the brain at a time. For example, using the fact that what is in our left visual field is only seen by the right hemisphere, they would show the right hemisphere a series of images very briefly, and then they would ask the patient to respond in some way. The tricky thing about these split brain patients is that they compensate for the fact that their two hemispheres operate independently by moving their heads so that anything they see or hear enters both sides of the brain. If you met one, you'd hardly notice that anything is amiss. So, in order to talk to one hemisphere without the other interfering, the psychologists studying the patients had to devise a clever apparatus that limits the information that each hemisphere receives. They could, for example, have the patient looking straight ahead and then flash a word to the left or the right and thereby control which hemisphere sees the word. Or they can put up a screen so that the patient can't see her hands and then present a set of objects to one hand or the other. With this apparatus, the psychologists could then get information from one or the other hemisphere. Every time you talk with someone, you're relying on the left hemisphere of your brain to keep up with and make sense of the exchange. So when the split brain patients were asked what they saw with their right hemisphere, often they would simply say, "I don't know," or "nothing," since the talkative left hemisphere didn't have access to what the right hemisphere was seeing. But then, if they were asked to choose from a set of alternatives, say by pointing to a picture of something that's associated with the thing that their right brain saw, or to pick up an object that matches the word with their left hand, they themselves would be completely surprised when their own left hand instinctively reached out and made a choice or responded to a command. In fact, they often felt as though they were just guessing. So, for instance, when the command rub was presented to the right hemisphere, the patient began to rub his head with his left hand. Or when the word walk was shown, the patient would push her chair away from the testing table and begin to get up. And here's what's really fascinating. When the patient was asked why he or she performed that particular action, the left brain, which dominates speech, spontaneously made up a story to explain the behavior. So the patient who rubbed his head was asked what command his right brain had been shown, and he responded by saying, "itch." But remember, the command was rub, but itch makes sense. And when the woman who began to get up from the table was asked why she was leaving, she responded by saying, "Oh, I need to get a drink." She didn't realize that her right hemisphere had seen the command to walk. Michael Gazzaniga was the first to suggest that in between these patients' actions and their responses, there's a part of their brain that interprets what they're doing. He called this storytelling function of the brain the interpreter, and he localized it to the left hemisphere along with language. Another term for this type of interpretation, this justification of an action without enough information to know for sure why it was done, is confabulation. The American Psychiatric Association's official Diagnostic and Statistical Manual of Mental Disorders defines confabulation as the recitation of imaginary events to fill in gaps of memory, or, in the case of the left hemisphere in split brain patients, gaps in knowledge. As my former mentor at the University of Toronto, Morris Moscovich, describes it, confabulation can be thought of as honest lying. Now, Gazzaniga found that confabulation in split brain patients occurred when the left-sided interpreter was forced to justify an action without information from the right hemisphere of the brain for why it happened. This means that when the left brain didn't know what the right brain was doing, it simply made up a story after the fact in order to explain the decision. And it was a story that the patient really believed to be true. These instances of confabulation in patients with commissurotomies give us pretty fascinating insights into how our own intact brains function. And by querying one hemisphere or the other independently, these patients have provided us with lots of information about what types of cognitive processes and information are localized in each of the two hemispheres in most people. But the most striking thing about split-brain patients is that it's really hard to tell from interacting with them that there's anything amiss at all. The truth is that both sides of the brain spend far more time working together and sharing information than operating independently in the healthy brain. And even in the split brain, the patient can compensate by moving their heads, for example, to ensure that both sides get the information they need to function. The experiments that demonstrate independent actions of the two hemispheres in the split brain patients have to be carefully crafted and controlled, because most of the time the patient will compensate for the cuts and just get the information each hemisphere needs by turning his or her head or making some other small behavioral adjustment. Even just by looking at the brain's connectome, the wiring diagram that illustrates the connections between different parts, it's abundantly clear that the two sides of the brain are intimately connected. That's why the left-right logical creative argument is largely a myth. They work together and are both necessary for complex thought. When we try to map the lateralization of functions, that is, when we design experiments to find differences between the left and right sides of the brain, we quickly realize how difficult this can be. The idea that the brain is strictly modular, that different brain regions have different functions, is no longer accepted in neuroscience. Instead, we talk about networks of circuits or regions that work together, and many of the circuits cross the line between the two hemispheres. What's more, patients who have had half of their brain surgically removed demonstrate just how malleable lateralization can be. Removing half a brain is called a hemispherectomy, and it's a last resort treatment for patients with a damaged hemisphere that is threatening or harming the rest of the brain. This situation can happen, for example, if a person has a malformed hemisphere that's taking up too much space and not functioning properly, like a child whose left hemisphere grew much faster than the right and is now pushing up against the skull and impairing the growth of the rest of the brain. Needless to say, hemispherectomies are rare. They're usually performed on children whose brains have a better chance of recovering function than those of adults. And it's well established that lateralized functions in the healthy brain, like language, can be rewired into the other hemisphere, especially if the patient is very young. This rewiring demonstrates one of the amazing superpowers of the brain, the ability to repurpose cortical real estate for important functions when the regions that are supposed to carry them out are damaged. This plasticity is seen both before a child develops the activity, for example, one born with just one hemisphere, and even after the function has begun to develop, as is the case in children who can already speak, but then undergo a hemispherectomy of the left side. The remarkable thing about these patients is that they can go on to lead impressively normal lives. So whether we're talking about split brain patients or children who have had a hemispherectomy, we see a reality that is very complex. We can't just say the left hemisphere controls analytical functions and the right hemisphere controls the creative process. It's just not that simple. And yet, back in the acting studio, I've been told to enhance my creativity by engaging in warm-up exercises that tap into right brain functions, like movements involving the left side of the body, or writing a sentence with the left hand, or some similar activity. It's really hard for me not to cringe in these moments, because the myth is so deeply ingrained, and yet so utterly wrong. It's possible that some of these tools can enhance creativity, but that's because they take you out of your comfort zone, or overturn stereotypic behaviors, or get your mind out of a rut. It's not because they're awakening your dormant right hemisphere. Your right hemisphere is chugging right along and exchanging messages with your left side all the time. And studies linking creativity to brain wiring have given us mixed results. Depending on how you measure and define it, some studies show that greater connectivity between the hemispheres enhances creativity, while others show the opposite. And this effect might even be different for men and women. In one study, men and women were tested for creativity using 4 divergent thinking tasks. The experimenters then computed a creativity index based on their performance. Male and female subjects didn't differ on average with respect to this score. But the relationship between connectivity and the creativity score was different for men and women. In the highly creative women, there was less connectivity between different brain regions, and more regions were activated by the tasks. The authors interpret this finding as suggesting that women recruit more of the brain when thinking creatively. Males, in contrast, showed more efficient regional activation and tighter connections between the regions involved. So which one is it? More modularity or more connectivity? The truth is that we're not even aware of the vast majority of what our brains are doing, even when we're considering important decisions or thinking creatively. Our conscious awareness is just the tip of the iceberg. And as Gazzaniga's patients show, our conscious interpretation of why we do the things we do isn't even necessarily true. The interpreter that we talked about a few moments ago is active in all of us. It explains our behavior by constructing stories from events we experience. It's our inner voice or monologue, and it helps us understand our own choices and ourselves. For split brain patients, the interpreter chooses to confabulate a meaning instead of admitting that it doesn't have one. And research suggests that all of us might be prone to confabulating, and we won't even know we're doing it. None of us is immune, particularly when it comes to justifying the many instinctual or intuitive decisions that we're forced to make every day. Just as Michael Gazzaniga's interpreter theory suggests, a part of our brain observes our behavior and constructs a plausible story that we then sell to ourselves as the truth. We relay that story to others, sometimes in surprisingly elaborate detail. And so, ironically, if this interpreter is primarily located in the left hemisphere, it just might be that much of our creativity comes from the construction of these left-sided stories. So, the bottom line is that the two hemispheres might divvy up some aspects of the workload, but they cooperate and collaborate much more than they compete. And while they each might have their strengths, most functions are dually represented in both sides. And finally, there's no evidence to support the notion that the left hemisphere is not intimately involved in the creative process. In fact, for many of us, it just might be driving the bus.